In this section of notes, we're going to be talking about dilations. And a dilation is a transformation in which a figure changes size but not shape. The pre-image and image of a dilation are similar. So if you think back to Unit 3, the pre-image and image are similar figures. The scale factor of dilation is the same as the scale factor of similar figures. So what you multiply the sides by the pre-image to get the image is the scale factor. A dilation with a center C and a scale factor N for a triangle JKL can be written as, so this is the notation for a dilation, as a capital D. You will have the scale factor in the first set of parentheses, and then comma what you're dilating it by, and then the figure that you are dilating. If a scale factor is greater than 1, then the dilation is an enlargement. If the scale factor is in between 0 and 1, then the dilation is a reduction. So if it's bigger than 1, you're making the figure bigger. If it's smaller than 1 but bigger than 0, so in between 0 and 1, then you're making it smaller. You're shrinking it. True or false? A dilation is an isometry. That would be false because it's changing the size. It's not an isometry because the definition of isometry is it doesn't change the size or the shape, it just changes the location. And then to find the scale factor, use the ratio of lengths of corresponding sides. Okay. So if we look at our first example, we're going to graph the image of each figure under a dilation centered at the origin with the given scale factor. And we're going to list their new coordinates below. For 1, we don't really have a graph, so we're just going to list the new coordinates. How you would do a dilation is all you do, and it's written right here. You're just multiplying the x and y coordinates by the scale factor to find the new coordinates. So if we look at 1, a prime, you're just taking the x and y values in A and multiplying them by our scale factor. Here our scale factor is 4, so that's what's written right there, 4. It's the first number in that parenthesis. So negative 3 times 4 is negative 12, and 4 times 4 is 16. B prime, again, same thing. You just take the x and y values and multiply them by the scale factor, 4. Negative 2 times 4 is negative 8, and 0 times 4 is 0. C prime, again, multiply everything by 4. 1 times 4 is 4, 0 times 4 is 0. And then lastly, D prime, 2 times 4 is 8, and 3 times 4 is 12. So those would be the coordinates of our new points, and then you would just plot them on a graph and connect. We don't have a graph, so we're just going to write it like that. In 2, it's the same concept. Okay? We have this point here, which is negative 4, negative 2, millimeter, and the scale factor is 3 over 2, because again, that's what's written first in the parentheses. So we multiply that by 3 halves. 4 times 3 halves, or negative 4 times 3 halves is negative 6. And then 3 halves times negative 2 would be negative 3. Okay. We have this point right here, which is negative 2, negative 2. And so again, multiply that by your scale factor, -2 times 3/2. Again, it'd be -3, -3. Our next point, this guy right here is +2, +2. So we multiply that by 3/2, we get 3, 3. And then lastly, for this point, we have 4, -2. So multiply both of those by 3/2, we get 6, -3. So now that we have our new points, we plot them. So we have -6, -3. We have -3, -3. Sorry, that should be positive. This is a +2. So it should be -3, +3. Thought that looked weird. And then we have 3, 3. And then lastly, we have 6, -3. And then we just connect. So here's our new shape. And if you notice, the fraction was bigger than 1. Because 3/2 is a decimal, 1.5, so that's bigger than 1, so we made our figure bigger. So that would have been an enlargement, as well as with the number 1, that was an enlargement as well, because the scale factor was bigger than 1. Okay, if we look at the next one, go ahead and graph that line if you remember to graph. Remember, the number in front of our x is our m, so that's our slope. So our slope is 2. Our b is where we start, and that's the back number, and that's -3. So when we graph it, we plot a point at -3 on the y, and then we just go up to right 1. 2, right 1, up 2, right 1, all the way across your graph. Then we go down to right 1, down to right 1. And then connect. Oh boy. We connect a little neater than mine. Graph. Okay? So what you're going to do is pick the points that you just plotted. So we had 6, 9. All those points you just plotted. Just like the last ones, find those points. We have 5, 7. We have 4, 5. We have 3, 3. Nope. We have 2, 1. 1, -1. Um, 0, -3. -1, -5. And then we'll just do one more. We have -3, -7. That's enough points. That should be enough. And what you're going to do is just multiply those points by the scale factor. So scale factor is 3, just like all those other problems. 6 times 3 is 18. 9 times 3 is 27. 5 times 3 is 15. 7 times 3 is 21. 4 times 3 is 12. 5 times 3 is 15. 3 times 3 is 9. So we have 9, 9. 2 times 3 is 6. 1 times 3 is 3. So then we have multiply that next point by 3. Multiply this point by 3. And then negative 3, negative 15. And then negative 9, negative 21. Okay? And you can only plot the points that are going to fit on your graph. So this guy right here, not going to fit, not going to fit, not going to fit. Don't worry about graphing those. But 9, 9 will fit. Here's 9, 9. And then 6, 3. And then 3, negative 3. 0, negative 9. And that's all that's going to fit. So there we go. If you notice the graph of the blue line, the first line, where the points were really, really, really close together. And then we multiplied it by a number that's bigger than 1. So that kind of stretches your graph out. And now if you notice, the numbers are further apart. If you also notice, these lines are parallel. Because those... And just to recap, my video paused and I'm not sure where it unpaused, but corresponding angles are always congruent. That is true because figures are similar after they've been dilated, so their angles are always going to be congruent. But their side lengths for the second statement are not, because you could have a small shape and then you made it big. Well, obviously they're not the same because one side is small, the other side is big. Corresponding side lengths are always parallel. We just talked about that in the previous example. That is true. Triangles are congruent. That's false, similar to that second statement. You could start out with a small triangle and move on to a big triangle. They're not going to be congruent. And then lastly, new figure will be the scale factor times as big or small. And scale factor times as far or close. That's true because you're multiplying that figure by the scale factor. So you're making it that much further and that much bigger. So those are the notes for that section. And there you go.